In the first semester, we talked about that there's different spheres of our planet. We have the biosphere, the hydrosphere, the geosphere, the atmosphere. And last semester, and the first semester, focused mostly on the geosphere. We looked at rocks, the rock cycle, we looked a little bit about how the hydrosphere, the water on the planet, influenced the rock cycle with erosion and weathering. We looked at a little bit about how the atmosphere impacted the geosphere, wind with our erosion and weathering, also with oxidation and causing some chemical weathering through that process. The second semester starts out with the atmosphere, and we're going to look at how does our atmosphere behave, what are the characteristics of our atmosphere, and how does that directly impact us. So obviously we need the atmosphere to breathe because it's where our oxygen comes from, but we also have our other characteristics of our atmosphere that influence us. We're going to look at how the hydrosphere impacts the atmosphere. We're going to look at how the sun influences the atmosphere. We're going to look at how, depending on if you're over the geosphere or over the hydrosphere, how that impacts your atmosphere. The big thing here is that our Earth is a system, and you can't just take one part out and say, this does the things that it does by itself in absence of everything else, because it doesn't exist in a system. In a system, all the parts are related, so all of our spheres of our planet are interrelated, and that's what we're going to be looking at this semester, is more of that connection. And we're going to do that through our study of the atmosphere. So our atmosphere is going to directly influence the weather and the climate of regions. Our atmosphere, once again, when we think back to our spheres, it's that thin layer of gases that surrounds our planet. It's been compared to a blanket. It's very thin. The part of it that we actually exist in, that has the oxygen that we need, the troposphere, is very, very thin. If you think of an orange, it is not the outside part of the peel, but you know that white stuff on the inside that you kind of peel off of the orange? That's the atmosphere in relation to the orange itself. It's very thin. There's less than 2 miles of area that we can actually live in off of the surface of the planet. It's actually closer to just over a mile that we can actually survive on our own without extra help in there. Within the atmosphere, we have daily occurrences, which is our weather. Is it raining today? Is it sunny today? That's our weather, those daily changing conditions. The climate is over the longer period of time. So we live in a desert. What is the average temperature? What is the average amount of rainfall? What's it like generally? That's more climate. So weather is very short term. Climate is very long term. So when we look at our atmosphere, most of you probably know that oxygen is not the primary component of our atmosphere. Oxygen is actually extremely flammable, and so we would be kind of in a lot of trouble if oxygen was the primary component of our atmosphere. We'd have a lot of spontaneous combustion if that were the case. Nitrogen, on the other hand, is what they call an inert, which means it's not reactive. It's not going to explode. There's lots of things that nitrogen doesn't do. It's a very stable element, and so it's good for us, and it's not poisonous to us in the levels that it's in our atmosphere. If we were to increase the oxygen too much, it actually would become a more toxic environment for us. We can't live all the time off of pure oxygen. I know that give people oxygen when they're sick and when their lungs are having trouble. We don't live off of that all the time. And like I said, it's very flammable, so we wouldn't want that to be our primary component, as we've got volcanoes erupting, as we've got all sorts of stuff that we as people do that provide sparks. We wouldn't want our atmosphere to be a larger component of oxygen. You'll see that we've got our trace elements down below. Carbon dioxide is actually a really small portion of our atmosphere. It fluctuates based on what people are doing, based on the amount of volcanic activity that's going on, the amount of vegetation that's around at the time. Those things will influence the amount of carbon dioxide that's in the atmosphere. So another part of our atmosphere that's really important to us is the ozone layer. The ozone layer exists in the stratosphere. It is a layer of of O3. Ozone is O3, So it's 3 molecules of oxygen that are stuck together. It's really important because it reflects UV light, okay, for us. So ozone, you probably have heard about ozone before. Ozone that's in the atmosphere is a good thing. Ozone that's at ground level is a pollutant. It irritates our eyes, it irritates our lungs, it causes plastics to degrade, it causes paint to break down, it can cause eye problems, it can cause, with the cornea and stuff like that, it causes health issues for people and other animals at ground level and for plants as well. So ozone at ground level, not very good. Ozone in our in our stratosphere, without which we would not have life on our planet because too much solar radiation would come down and it would basically fry our planet. So we really are happy that the ozone layer is there. We cannot take ground level ozone and make it stratospheric ozone. It doesn't work that way, unfortunately. And some of the contaminants that we make here on the surface, as they rise up because they're lighter, and they rise up through the atmosphere and they get up to the stratosphere, they can actually break down the ozone layer. So we've got to be careful about the chemicals that we produce at ground level, make sure that they're not damaging that ozone layer up in our stratosphere because that could have extremely negative consequences for us. This is what I was just saying. Some of the things we don't use anymore, the aerosol cans, it was the propellants. It was the thing that they put into it that made the hairspray come out. That was the stuff. There are chlorofluorocarbons, and they were the propellants, and they were a component of the propellants, and we don't put those in aerosol cans anymore. So that's one area where they used to come from that we figured out that it wasn't such a good thing. When they developed chlorofluorocarbons, they thought that they were the greatest thing because they were non-toxic. They were relatively easy to make. They didn't see any negative side effects for like 30 years. And then they realized, oh wait, when the chlorofluorocarbons go up into the atmosphere, the fluorine actually detaches itself and it attacks goes after the oxygen. It breaks one of the oxygen away from the O3, so now you've got O2 and just a single O. And then it releases, actually it's the chlorine, excuse me, the chlorine attacks it, and then the chlorine will release itself from the oxygen, and it will go attack another one. And so the chlorofluorocarbons that we put up into the atmosphere are still actively breaking apart our ozone. So we want to make sure we're not putting more up there. The coolant, it is still actually in coolants. So that's one reason why if your coolant is leaking, you're supposed to go get it fixed. And only people with special equipment are supposed to take care of our air conditioners and things like that on our cars. So last semester we talked just briefly about water cycle as it related to erosion and weathering. So you have raining, right? And then you get runoff, and that carries away dirt, and as the water is hitting the surface of the soil, it can cause it to pick up and move away. But water's not the only thing that cycles. Oxygen cycles, the oxygen-carbon cycle, where we go through photosynthesis and transpiration, is actually moving that carbon dioxide and the oxygen through our atmosphere, and that's a really good thing. Nitrogen cycling will pull nitrogen in plants, and there's bacteria that's on their root nodes that it's a mycorrhizal fungi. It'll actually fix nitrogen out of the atmosphere into the soil because plants can't just use nitrogen through their leaves, can't like take it in through their stomata, the little openings in their leaves. They can't take it in and use it. They actually have to have it fixed in the soil for them. They have to have something help them out. And then they're able to use that nitrogen. When they break down, they do release nitrogen back into the soil. Some of it goes back up into the atmosphere. And so it's cycled through. Nitrogen is an important fertilizer for our plants, so it's really important that our plants can also fix nitrogen out of the atmosphere and not just rely on chemical fertilizers. There's other things also not on this slide. Sulfur cycles through the atmosphere. Phosphorus cycles, but it just doesn't cycle through the atmosphere. Phosphorus cycling happens through the rock cycle. All right, when we talk about our atmosphere, the atmosphere puts pressure on the surface of the Earth. So I want you to imagine the Earth. You've got your circle of the Earth. Gravity is greatest at the center of the planet. That is where, because of the spin, the gravitational pull, our planet is spinning, and which means that it's trying to push things out. But gravity is pulling it back in. So if you've ever been to like the fair or to a carnival or something like that, and they used to have this ride that was called the Gravitron, and I think it has a different name now, but you stand in it and the whole thing spins, and then you're like stuck to the walls. You can lift up your arms and stuff, but you stay stuck to the walls as long as the ride is spinning. And that's kind of how our planet is. Because our planet is spinning, it's trying to push stuff away from the planet, but gravity is stronger right now and it pulls it back in. So where those things balance out is our atmospheric pressure. So the amount of atmospheric pressure is greater as you are down at lower altitudes. So the closer you are to the surface of the planet, where gravity is the greatest, it's going to pull more on the air down there. So you have higher air pressure down closer to the ground. And you have lower air pressure as you get up into the higher altitudes. We also have our atmospheric pressure changing because of storm systems coming through. So when we get rain here in the desert, usually it's because an area of low pressure has moved in over the area, which means that the warm air has risen and it goes up through, then that warm air rises up, it's got some moisture in it, and so it's able to rain. It's able to cool and condense and then rain. So we've got areas that have low pressure because a storm has come through, and we've got areas that have lower pressure because it's at the top of a mountain, for example. Now, the lower the air pressure is, the further the molecules of air are apart. When you're up at higher altitudes, that means that the air is thinner, it's harder to breathe, you have to work harder to get the oxygen into your lungs. It also means that it's usually cooler because the air molecules are further away from one another. And the thing that creates temperature is when the air molecules are touching one another and they're rubbing up against one another, just like if you were to take your hands and you rub your hands together and they warm up because of friction. That's the same reason why the air temperature goes up, is the air molecules are rubbing up next to one another. So your higher altitudes, you have less air, less particles, so they're not rubbing up against one another, and that's one of the reasons why it's colder. Even though it's closer to the sun, it's colder because the air molecules are further apart. You are going to be doing an exercise with atmospheric pressure in one of the assignments, so you'll get to play around with the atmospheric pressure a little bit. We measure that through a barometer. So this is an example of one kind of barometer. There's other kinds too, but basically what happens is the bottom of this tube is flexible. And there's mercury or a dye or something like that that's in there. And because it's flexible, the greater the air pressure is, the more it can squeeze the bottom of that together and push the fluid up through the barometer, and then it's kind of like a thermometer. So it raises up, and you get millibars of mercury, and that's how we measure air pressure. So the greater the air pressure is, the further the mercury is going to go up the tube, and it'll tell you that the air pressure is greater. When it's falling, and there's not as much pressure on it, it's going to relax its grip, basically, on the bottom of that tube, and the mercury is not going to go up as high. So here's another kind. This one is an aneroid. It doesn't have any liquid in it, but the back of it is a flexible piece of metal, and so it actually allows the back of it squishes in as the air pressure goes up, and then it spins the dial. So here's our atmosphere. So down here towards the bottom is the troposphere. This is where all weather occurs. This is the part of it that's important to us because it is where all of our oxygen is. It's where the conditions are right for human life to occur, for all life to occur. As we get up a little bit further, here's our ozone layer that we were talking about. It's in the lower part of our stratosphere. We've got our mesosphere above that and thermosphere. So they're named differently by their height above the surface, their temperature, and the amount of air pressure that's in there. Our exosphere is basically that last stop before we get to outer space. Doesn't really mix a lot between the layers. We're going to talk about the layers a little bit more. These are the ones that you're going to be responsible for knowing. You need to know the characteristics of these 4 layers: the troposphere, the mesosphere, the thermosphere, and the stratosphere. So once again, our troposphere, closest to us, but if you look at it, the elevation is not very high. Look at how small it is. Remember I was saying that there's only that very thin layer around the planet where we can actually live. You can see as you go through the troposphere that the temperature starts to change. As you get higher up, it starts to get colder. Our stratosphere is next, sitting on top of our troposphere. Also not very thick as our stratosphere, but really important, contains our ozone layer. We talked about how that protects us. Our mesosphere is our next layer. So in these ones, you're going to order. The thermosphere heats up. It's the highest layer before we get to the exosphere. It's where we get our shooting stars that come through, right? Which is our meteorites that are burning up in our atmosphere. That's where we see those. If you've ever had the opportunity to see the aurora borealis or the northern lights or even the southern lights, this is where radiation from the sun kind of skips off our atmosphere and it makes that pretty, pretty light show.